So that's what we'll be covering today and tomorrow, is what's going to be on that. So, because that's Friday. I gave you that earlier because since I didn't know if you were going to be back when this week, just in case. All right, guys. So we're continuing on from chapter 3 because chapter 4, that green book, was just kind of an in-between. Now this here, polynomial functions, is what we're going to be starting with this here. Now quadratics are a polynomial function, but we're expanding out because there's more than just quadratics. So this first page here, recall that a monomial is a number, a variable, or the product of a number and one or more variables. A whole number, exponent. A polynomial is a monomial. That is a sum of monomials, sum of multiple terms. A polynomial function, this here, classifies any and all types of polynomial functions, where our a sub n, a sub n minus 1 is just a number. It could be the same number, it could be different numbers, but we're just saying that a is a number. Could be different, could be the same. X to the n, where n is just a number. X to the n minus 1, so if we said n was 4, so we have x to the 4th. X to the 4 minus 1 would be x to the 3rd, and just decreasing down. Now, here are 4 types, or really 5 types of polynomial functions. So if the degree is 0, we just have a number. So f of x equals negative 14. X equals, f of x equals a number. Linear, equation of a line, 5x minus 7, because the biggest exponent attached to a variable is 1. Quadratics, which we covered in the last 2 chapters. We call it a quadratic because the degree is 2. The biggest exponent attached to a variable is 2, so it's a quadratic. The one after that's cubic. The reason we call it cubic is because the degree is 3. The biggest exponent attached to a variable is 3. And lastly, quartic, because the biggest exponent is 4. We kind of get how this works so far, yes? Now, defining or classifying polynomial functions, or kind of if we're going to write them out. If we write it in standard form, writing a polynomial in standard form is writing it in decreasing degree from highest to lowest. So whichever variable has the biggest exponent goes first, second, third, fourth. So they're just decreasing. So we'd have x to the 4th, x to the 3rd, x squared, x, constant term. And the leading coefficient is the number in front of the term with the highest power. All of the numbers in front of variables are coefficients, but the leading one is the one in front of the variable with the biggest exponent. Questions on this so far? All right. Now we need to determine what is a polynomial function. Well, there's ways we can go about trying to classify what it is. I think it's better to try to figure out what it's not. What does not make a polynomial function? First thing is, exponents aren't negative. We cannot have a negative exponent attached to a variable. Technically, we can have one attached to a number. We can have 2 to the negative 1, but we cannot have a negative exponent attached to a variable. So we can't have x to the negative 2nd power. This is not a polynomial function. No, you're good.
Take advantage.
All right. Yeah. It's not hard to slam that door. For some reason, it doesn't take much. Exponents aren't fractions. And again, all this is mainly attached to variables. We can't have x to the 2/3. You can't have fractional exponents. exponents aren't variables. Exponents aren't variables. Now, this could be attached to a variable. We can't have x to the a. We also can't have 2 to the x. We cannot have a variable in an exponent. And part of the reason for that is, well, these are considered exponentials, not polynomials. Questions on any of this here? Pay attention. Questions on these three so far? Our next one. And let's try this again. Variables aren't inside of radicals. Can't have square root of x. We can't have variables being multiplied together like x times y. They have to be different variables like this here. I mean, technically x squared is variables being multiplied together. We can't have different variables is the key thing. X times y does not work. And lastly, variables cannot be in the bottom of a fraction. Yeah, because in the top of fractions, just x over 1, 1/2 x. It just cannot be in the bottom of a fraction, because if it's in the bottom of a fraction, it's not considered a polynomial. It's actually rational. It's a rational function. Questions on these here? All right. So let's look at these examples here. So the first thing is decide whether each function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. So we want all that there. So if we look at number or letter A, negative 2x cubed plus 5x plus 8. So we want to go through all those. Here, our exponent's negative. Well, no, we don't have a negative exponent attached to the variable or any of the exponents. Fractional. Is there a variable inside of a radical? Do we have two different variables being multiplied together? Is there a variable in the bottom of a fraction? No. And I think we can go through the whole list. None of those. So is this a polynomial function? Yes. So if we write in standard form, well, we want the variable with the biggest exponent first, which is our x to the third. If we don't have an x squared term, that's fine. Our x to the first, the 5x would go next, and then 8. So this is technically already in standard form. We really didn't have to do anything to it. Now the degree is the biggest exponent attached to a variable, which is what? 3. Now the type is connected to this degree. Since this is a 3, it would be cubic. And lastly, leading coefficient is the number in front of the variable with the biggest exponent, which would be -2. Okay. Questions on this here? And that's all we have to do for A. Now let's look at B. Is B a polynomial function? It actually is. And there's a reason for it, because what we're thinking the reason it might not be is this square root of 2x to the fourth because of the radical. Now, if it was like this here, yes, it's not a polynomial function because the variable would be inside the radical. And they did this on purpose to see if you'd pick up on that or not. So here the variable is technically outside the radical, so yes, this is still a polynomial function. But it's not in standard form, because our first term in standard form would be square root of 2x to the fourth, or x to the fourth times the square root of 2. Both of those are fine. And really, just so we don't confuse ourselves, we can say x to the 4 times square root of 2 minus 0.8x cubed minus 12. Now, what's the degree for this here? The degree would be 4, which is a quartic. Our quadratic is our degree 2. Our quartic. And the leading coefficient is square root of 2. I just wrote it that way because we can write it square root of 2 because it's just multiplied together. Because that is the leading coefficient, I put it in front so we make sure that we don't put it inside the radical because it's technically out. But we could write it either way. Questions on A or B? C, negative x squared plus 7x to the negative 1 plus 4x. Is this a polynomial function? Not a polynomial because of our x to the negative 1. We cannot have a negative in the exponent attached to a variable. So that's out. And that's all we have to do. Because it's not a polynomial function, we don't have to write it in standard form, state, degree, type, or leading coefficient. And the last one on this here, letter D. No. Exponents can't be variables. Not a polynomial. Questions on these here? Be ready for the next ones. We'll do 1 and 2 because I think we're kind of getting the hang of this. So 1, can we say this is a polynomial function? Yes. Standard form, f of x would equal what? Negative 1.6x squared minus 5x plus 7. The degree would be 2, because exponent, biggest exponent attached to a variable. And since it's degree 2, it is a quadratic. And the leading coefficient, negative 1.6, because we're looking for the number in front of the variable with the biggest exponent. Number 2, we have x to the negative 2, so not a polynomial. Questions on any of this here? I think we feel good with these here, yes? I'm not going to worry too much about that one because it is a polynomial. We would rewrite in standard form of 3x to the fourth plus x cubed minus 6x. The degree is 4, so it's a quartic, and leading coefficient is 3. Let's look at example number 2. We want to evaluate this function here when x is 3. So all this means is that we're going to replace every x in this expression with 3. We can plug that whole thing into the calculator. Yeah, 98. That's what I got too. But yeah, no. All you gotta do is type these in the calculator, it'll give you your answer. It also did help that I knew 3 to the 4th and 3 squared already. But yeah, it's just typing it in, solving. Because if we wanted to evaluate this when x is -4, all we're going to do is -2 times 4 to the 4th plus 6 times 4 third 3. Now 4 to the 4th is 64 plus 6 is, no, 4 to the 3rd is 64. Because 64 and 64 is 128, 256. Could be 4 to the 4th. 3 times -3 times 4 is -12 plus 11. 2 carry the 1. -5, 12. 4 carry the 2, 38. Minus 1. 8, 9, 2. Did you also get -129? Okay. Questions on this here? Do we need to see another example of plugging these in? No, and especially we need to be careful when the value of x is negative in putting parentheses around it, because our even powers is going to cause it to be positive. And if you don't put the parentheses around it, it's going to give you a negative value instead. Now, there is also something interesting with these higher degree polynomial functions, is that they have a certain in behavior. And all this means, and especially if you notice, well, let me get a highlighter. There's a reason that everything in the center is this dashed line. It's not saying it's not equal to it, but what happens in that section is going to vary depending on the function. So sometimes it will make that exact shape, sometimes it won't. But what's interesting is that as we get far enough away from the center, it will start behaving in one of these 4 ways. If our degree is odd and the leading coefficient is positive, at some point, as we go to the left, as we're going in this direction, the graph will eventually head down. It's going to go towards negative infinity for the y. And as we go to the right, towards positive infinity, it's going to go positive infinity. Our f of x is just our y value. So degree is odd. Degree even. Leading coefficient, positive. Since the leading coefficient is positive, as f of x approaches negative infinity, as x approaches negative infinity. And f of x approaches positive infinity as x approaches positive infinity. Okay. And that's the first one there. Now also, if the degree is odd and the leading coefficient is negative, now as we go to the left, as x values get smaller, f of x is going to go to positive infinity. So we can say f of x, leading coefficient, approaches negative infinity as x, or positive infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. Now with even is our quadratic, our x squared. Eventually they're both going to either go up or down. And as the degree is even and the leading coefficient is positive, both ends are going to end up going up. So we'd say f of x approaches infinity as x approaches negative infinity, and f of x approaches infinity as x approaches infinity. And with the leading coefficient being negative, they're both going to go down. So f of x approaches negative infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. And it's just describing how is the function going to behave eventually. Now the reason we have this is to help us figure out what kind of solutions we can have. Where's the function going to be going? So let's actually put this into context. Now for us to be able to do any of this here, we need to figure out two things. One, our degree and leading coefficient. So what's our degree for this here? It is 4. And 4 would be even, because it's an even degree polynomial function, because the degree is 4. Leading coefficient is what? 0.5, so this is negative. So it's even and negative. Okay? Degree is even, leading coefficient is negative. So our end behavior is this here. F of x approaches negative infinity as x approaches negative infinity. F of x approaches negative infinity as x approaches infinity. And that's it. That's the full answer. That's all we have to do. Questions on this here? Because really all we're saying, as we go from positive to negative infinity, as we get bigger and smaller values of x, what are the y values going to do? Because they're going to act in one of 4 ways. They're either going to go to positive infinity or negative infinity. Let's look at this one here, the end behavior of this graph. Well, the degree is what? 3, so it is odd. Leading coefficient is so negative. So we have odd and negative. So now we just need to look at that table for odd and negative, and that's our answer. And it tells us that f of x approaches positive infinity as x approaches negative infinity. And f of x approaches negative infinity as x approaches positive infinity. And that's it. That's all we have for this here. So really, end behavior is completely based off that chart. How is it going? And we can use that chart to just answer. We just look at the chart, determine is the degree even or odd, leading coefficient positive, negative. And we fill in the corresponding information. Questions on this here? We feel comfortable with end behavior. That's it.